Welcome to the next lecture of 3D and methods that's concerned about electron tomography or cryo-electron tomography. As you may already heard about computer tomography, which is a kind of medical device that is used for 3D visualization of patients. Here what we have is a tunnel. Inside the tunnel we have an X-ray tube and a detector. The X-ray tube is rotating together with a detector and taking a series of images of the patient, which then can be reconstructed back to 3D to visualize the sections of the patient. The advantage of computer tomography is that it can rotate all the way around 180 degrees the patient and take a full so-called CT scan. We also have electron tomography, for which we obviously use electron microscope. This tomography is analogous to the computer tomography, but we are not using X-rays here, we are using electrons, and these electrons are irradiating our sample. We are taking a series of tilts of our sample and recording it on the detector. Because for every tilt, we actually know what's the tilt angle at which the sample was collected, we can assign these angles to our recordings, and after that we can back project the recorded 2D images into a 3D volume. Now, if we compare tomography with single particle analysis, we can find few advantages of a single particle analysis as well few advantages of tomographical analysis. For single particle, as we already discussed from the previous lecture, we are taking only a single projection image of the sample. That's only one 2D projection of our sample, and so that image only contains information about one orientation of our sample. This is of course useful if we have small sample that are many of our sample molecules are located in the view field area, and we are assuming that these molecules are oriented in random uniform orientations, so that if we collect enough 2D images, we can assign the angles of the rotations, we can reconstruct a 3D reconstruction. Because we are exposing a single acquisition area, we have higher signal to noise ratio, yet in cryo-EM we are still at the very, very low doses, and therefore the signal to noise ratio is still very low. Single particle analysis is not suitable for samples where 3D information from single acquisition area is needed. For example, if we take a cell, we simply don't have enough uniformly distributed cells that we can average together and make a 3D reconstruction using single particle analysis. We can do it for parts of the cells, but if we want to make a whole reconstruction of a cell, we cannot do single particle analysis because simply we would have only a single 2D projection of the cell. And what we know already is that the sample needs to be electron transparent, because otherwise we can't make the projection images. In case of tomography, we are taking multiple projections of the images at different tilt angles. Therefore, we know the tilt at which we collected the recording, and that we can back project and make a 3D reconstruction. The problem that we are exposing multiple times the same area is that we need to lower a lot more the doses than what we are using for single particle analysis. This gives us even lower signal to noise and therefore more hazy output. One difference between the single particle and tomography analysis is that for tomography analysis we don't have the ambiguity in the handedness determination. If you take a look on the right, we have a left and right hand, where we on the first image see the back of the right hand, and on the other image we see the palm of the left hand and the palm of the right hand. And if we take a projection image of these two hands, we will get in fact the identical output, so we cannot distinguish which hand we are imaging at all, if it's the right hand from the top or the left hand from the bottom, or vice versa. In electron tomography or in tomography at all, if we tilt our sample, we can distinguish whether we are looking at the left or the right hand, because we get different relative positions in between the fingers. So you can see that the thumbs and the little finger are pointing towards different directions under the same tilt. If you take the projection image under the tilted angle, then you can clearly distinguish what's the handedness of your sample. Tomography, in fact, as same to the single particle analysis, needs a sample that's electron transparent, but because we are studying usual different samples than for single particle analysis, we need to achieve this by some different sample preparation. Sample preparation for tomography can be the very same as it is for single particle analysis, that we have a purified sample, we plunge freeze the purified sample in liquid ethane, and we collect cryo-EM SPA. This can be used for purified macromolecules, for purified complexes, that then can be used for sub-tomogram averaging and tomographical analysis. Yet, very often we are using cellular samples for the tomography, as we discussed, that it's very suitable for that. And for cellular samples, we can have thin samples and thick samples. The thin samples are cells that are thin enough to be electron transparent, some bacteria, some transparent parts of the eukaryotic cells. These cells then we can plunge freeze and readily use for the cryo-electron tomography, or we also can plunge freeze them, and because they are thin enough for plunge freezing, and then use cryo fib milling in the SEM microscope to thin more, to make it more electron transparent, for example, creating some lamella. If we are very thick cellular samples, like tissues or thick cells, we cannot plunge freeze them in liquid ethane, because that would lead to devitrified ice, non-vitrified ice that's crystalline. We need to use high pressure freezing that we already discussed in the preparation part of the lectures, or the sample preparation lectures. And these high pressure frozen cellular samples, we can further cryofib mill to make them thinner, or use cryo-ultramicrotomy for thinning the sample. We will get some sample that's thin enough for the further cryo-electron tomography. This is just to show the same thing more in images. If we have, for example, some virus sample or a protein sample, we can really plunge freeze it, don't need any thinning, and we can use it for the electron tomography. That's the same for many of the bacteria, that those are thin enough for the acquisition process. Yet for cells, we can have very thin parts of the cells, like the lamellopodia, that you can use readily after plunge freezing for tomographical analysis. But the middle part of the cell is too thick for that, and for that we need to prepare a thin sample that's usually done by fib milling, whereas we are milling away the top and the bottom of the cell using a focused ion beam, and create in the middle a thin enough lamella of around 100 to 200 nanometers. This is transparent, and then we can record these cells as a tomogram or a tilt series for tomographical reconstruction. And if we are even thicker samples, like tissues, we can high pressure freeze these tissues, and then either do some lamellas out from them, or we can mill out a piece of this tissue and lift it out in the SEM, place it into special grids. This is a kind of state-of-art processing of the cell tissues for cryo-electron tomography. Now for cryo-electron tomography, we have a little bit different acquisition scheme than we had for the SPA. For SPA, we usually are aiming for large amount of micrographs, where every micrograph is a single shot of a single place, and we are doing it under different foci to be able to fill the gaps in the contrast transfer function where it's crossing the zeros. For acquisition of the tilt series, we need to acquire a tilt series actually, which is the same area that's exposed multiple times. That means that there is a higher radiation damage on the same area of the sample than for the SPA it would be. Therefore, we need to decrease the electron dose, and we need to decrease the electron dose very highly, so that we end up with a 2 to 3 electrons per square angstrom electron dose, whereas in the SPA we were in the range of 50-60 electrons per square angstrom. But because we are collecting around 41 tilt series, then we need to multiply this electron dose per every tilt, so that by the end our sample will get a dose around 100 to 150 electrons per square angstrom. For that, we have special schemes for acquisition as a dose symmetric. We will discuss it a little bit later. Because nothing is perfect, our stage is not perfect, and we want to precisely track the tilts, it's feasible to include some so-called fiducials into the sample. The fiducials are small gold beads that are allowing us precise tracking of the tilts. These small gold beads of size 5 to 10 nanometers are making a very dark spots, contrastful spots in the sample, and these are very easily trackable even under low doses, and therefore we can reconstruct how the tilts were moving during the acquisition process. Depth focus during the tilt series acquisition is usually kept constant, because we will discuss later that actually from a single tilted sample we have information at different defoci, because there's a gradient of defocus in each tilt series. And one last thing that we need to be aware of, that we need to properly align the tilt axis and properly set the eccentric height to the area of our interest, because for the tilt series this is very important, and I will show on the next slides why it is so. So if we insert our sample into the microscope, this is a classic sample holder, and by the very end of the sample holder we have a sample on a classic electron microscopic 3mm electron microscopic grid, and from here we have the electrons that are irradiating our sample, and of course our sample is immersed in the objective lens where we have the pole pieces, and the sample is rotated in the electrons. This is how the tilt series are collected. Now, every holder is inserted in so-called goniometer, and the goniometer is an instrument that's able to vertically align the center of rotation of the sample. This is what we usually call the z-height, and that's how we can tune the eccentric height of the sample. Why it is important? Let's take our sample that's perfectly located on our tilt axis, and the tilt axis now is facing towards us, so it's in the perfectly aligned on the z-axis, and we start to tilt our sample. This red represents the sample plane. So when we are starting to tilt our sample, we see that our sample is still located on the tilt axis, and we can tilt it to the positive or negative tilts. The sample still remains on the same place. This is when the tilt axis doesn't have any offset, so the offset of the tilt axis is 0. But what happens if our tilt axis will have some offset? So now our sample plane is higher than the tilt axis, so there's some offset. Now we start to rotate our tilts, and what we see that not only that the sample plane is inclined, the sample is also moving away from the center of interest. So the more and more we are rotating our sample around the tilt axis, and plus we have some offset of the tilt axis, we are moving also our point of interest. Now we can see we have some lateral movement Plus, we have also a movement in the z-axis. This is this will cause us a change in defocus, and this will cause us a movement in the xy direction. That means that our sample might get out of the field of view, so that we will not have all the information for the reconstruction of our sample. Nevertheless, I have to say that we never have perfect stages. We are never able to perfectly set the tilt axis without any offset. So we need to correct for this. And this is corrected the following way. Usually when you are acquiring tomographic or tilt series data, you have your acquisition area, and close to your acquisition area, you have a focus and tracking area. The focus and tracking area serves to precisely track the position of your acquisition over the tilt series. So after each tilt change in the tracking area, you are taking an image and cross-correlate the image of this tracking area with the previously known image of the tracking area from the previous tilt and make some corrections. If you see that by cross-correlation that it shifted, then you make a correction in shifts so that your data acquisition area will be acquired at the same position. Also, as we told, that the offset in the tilt axis causes defocus change. At the same area, you can make some focusing and set the defocus exactly to the same value as it was on the previous tilt. So how the acquisition itself works: you perform a stage tilt, you take a tracking image, you cross-correlate the tracking image with the tracking image of the previous tilt, then you know what beam shift corrections or image shift corrections you need to perform to have your data acquisition area at the same place. You perform focusing to know how the focus offset changed, and then you make a tilted image acquisition. And this is the thing that you are doing over and over while you finish your tilt series. One very important thing is that the focusing and tracking area has to be placed on the same axis as the tilt axis is. So this axis, what you can see here, is actually the tilt axis of your image. The image is rotated around this axis. It's not always and almost never perpendicular to the axis of your image, either X or Y axis. But you have to be sure that your focusing and tracking area is on the same axis as the data acquisition area, so that you don't have any differences in the focus. Because if that would be somewhere here, then by tilting your image and this part would come higher, the defocus here would be different than the defocus in the data acquisition area. Why we are not focusing and tracking at the data acquisition area? This is because we don't want to burn our sample. We don't want to make more radiation damage than we have to do. And also for the tracking and focusing area, we are usually choosing this area at the place of carbon, which is, let's say, richful for contrast information. And also we can apply more dose on these parts. Now, tilt schemes. Because we already discussed how we acquire our tilts, we also need to discuss a little bit what are the tilt schemes and how we can acquire actually our tilts. There is not just a single solution. There are many ways how you can acquire a tilt series. Here are 3 of them shown, and we will then discuss more this dosimetric one. What you can see here is the representation how the tilt series are acquired in an unidirectional tilt scheme. Here the most blue tilt is the tilt number 1, and the most red tilt is the last tilt number 41. Here we have a tilt series of plus minus 60 degrees, and we can see that we start at plus 60 and gradually moving to minus 60, crossing the 0 point. So we start at 60 and we go to minus 60 by the increment of the steps that we defined. This is the unidirectional tilt scheme. There's a different one. This is called bidirectional tilt scheme, where you can see that the coloring is different because here we start at 0, then we follow in one direction till we reach the highest tilt in that direction, for example, the 60 degrees. Then we return back to 0, and then we are tilting in the negative way up to minus 60 degrees. So we can see that here we cross the 0 2 times, yet only once expose the 0 exposure, actually. And then we have the most, let's say, complicated one, the dosimetric tilt scheme, where we are actually starting at 0 and then taking 2 tilts in the positive direction, 2 tilts in the negative direction, and then again 2 tilts in the positive direction, 2 tilts in the negative direction. This is the so-called dosimetric tilt scheme. Actually, the original dosimetric tilt scheme is defined as 0 and plus, then minus, minus, plus, plus, minus, minus. Sometimes some people are using the 0 as an extra value, so they are taking 0, plus tilt, minus tilt, minus tilt, plus tilt, minus tilt, minus tilt. Why it is important to have this dosimetric tilt scheme is because what's happening when we are tilting our sample is that we are changing the sample thickness. And what we know that when we are serially exposing our sample, then the first tilts are getting less radiation damage or less radiation, and therefore are less damaged than the last tilts. So those over the tilts are accumulated. Because the last tilts, the tilts that have the higher angle, gives us also the sample that's thicker, because we can see the sample thickness here at 0 tilt is different than the sample thickness here at 60 degrees. We see less useful information in higher tilts because the electrons has to pass through a more dense material, and therefore they are carrying less information. In the dosimetric tilt scheme, what we can say is that we will collect the low angular tilts as first, because they contain the most useful information for us, whereas the higher tilts, the extreme tilts, are carrying less useful information, and therefore we are not caring that much about the radiation damage that we applied using the accumulated dose. So this way, in dosimetric tilt scheme, we can use more information from the lower tilts because of less radiation damage, less information in the higher tilts, yet in the higher tilts the amount of information is also limited because of the thickness of the material. Here is just to show you how the radiation damage looks. Here we have a cell that's exposed at 1 electron per square angstrom, and we can see that this cell has a very, very low contrast. If you want to have a higher contrast, we can expose the 10 electrons per square angstrom, and that looks fine. Nevertheless, we have to take care about that for our tilt scheme, for our tomographical analysis. We need to expose this area several times. And for example, if we would expose our area 10 times by 10 electrons per square angstrom, we would end up in 100 electrons per square angstrom in 10 tilts, and we already see the radiation damage inside the cell. If we go even higher, we can see that at 300 electrons per square angstrom radiation, we see already the bubbling and we destroyed our sample of interest. Therefore, we need to find a correct balance in between the amount of the electrons that we need per single shot. We need to properly set up how many tilts, what will be the tilt step of our tilt series, not to damage radically our sample. Now, the acquisition setup itself, well, we know how the acquisition works. We need to choose our angular increment, the maximum tilt angle. That means how many tilts we are going to acquire. Therefore, how we need to set up our tilt dose per tilt. Here, for example, if we choose plus minus 60 degrees rotation per 3 degree step, this will end up in 40 tilt series, 40 tilts per series, plus 1 tilt for the 0 angle, so in total 41 exposures. We will discuss a little bit later, just a few slides later, why we can acquire in single axis or dual axis mode. In general, we are acquiring in single axis where we are tilting only one axis of the sample. Camera setup, because in contrary with the SPA, here we are not aiming that much on the speed, because we are not limited by the speed of the camera here. We are limited by the other steps of the acquisition. As we told, we have the steps of focusing, tracking the image. These steps and also tilting the sample, these steps are more time consuming than actually the acquisition of the sample. So what we can do is to decrease the frame rate of, for example, the K3 camera, which was support for the so-called correlated double sampling mode, the CDS mode. And in this mode, the camera should have even better signal to noise ratio for the counted electrons. We usually use very short exposure times because we have only 2 to 3 electrons per square angstrom. On K3, this leads to 0.5 second to 1 second exposition, depending on the setup of the electron flux. And because we have only few electrons per movie, if we are acquiring in movie mode, which is highly recommended, then we are usually fractionating it into very few fractions, around 4 fractions. Where even in this mode, if we fractionate the 3 electron per square angstrom into 4 fractions, we will get less than 1 electron per square angstrom per fraction information in the image, which still should be doable for the motion correction or drift correction in later steps. Another thing that's very useful to have if you are doing tomography for a microscope is energy filter. As you already told about high tilts, have thicker sample naturally because we are inclining our sample, and the more thick our sample is, the more inelastically scattered electrons are present. And the inelastically scattered electrons are not carrying information about our image. They are carrying more noise. So if we can get rid of them, that's very feasible to have an energy filter set up in zero loss mode and with a slit set to 10 to 20 electron volt gap. This will increase our contrast of our acquired images. If we can use faceplate. We have very low dose images for the tilt series. Therefore, if we want to increase the contrast, we can increase it by even a higher dose, which is not feasible for the tilt series acquisition, or we can compensate by higher defocus. If we want to keep the defocus as low as possible, we can use, for example, Volta faceplate. That will give us comparable contrast at lower defoci than is usually used when applying high defocus. And the last thing that's nowadays very used is combining of SPA and tomography, where we take an advantage, as we talked about, that at zero tilt, we have the most transparent sample. The sample is carrying, this shot of the sample is carrying the most useful information. So what we do is that at zero tilt, we will acquire the first tilt at a higher dose, 10, 20, even higher dose rate. And this will not serve us only as the zero tilt for tomography, but this will serve us also as a micrograph for an SPA analysis, where we can correlate our results from a tomographic reconstruction with a reconstruction from SPA that's kind of more established than the tomography. Other tilts, however, in this case are acquired with the so-called standard dose, a lower dose, not to have extensively high radiation damage. Here is just showing off how the energy filter works. We have a field emission gun that has a very, very narrow energy spread. What happens when the electrons are interacting with the sample is that there are elastically scattered electrons, which are scattered by the sample elastically and carrying information about our sample as image data. And then there are inelastically scattered electrons which interacted with the material, therefore they lose a little bit of their energy. and therefore they are not contributing to the image data. Using a prism, we can split these electrons with different energies to different places, and then using the slit, correctly set up slit, we can filter out these electrons to let only the elastically scattered electrons hitting the detector. And for Volta's faceplate is doing phase shift in the CTF curve, and the higher the phase shift is between the unscattered and the elastically scattered electrons, which phase shift is very low for the samples without the faceplate, the higher contrast we get. Here we can see a nice show of fiber at -5 micron defocus without Volta faceplate, or this is some flagellum, sorry, at -5 micron defocus without faceplate, or an image that's in focus without any applied defocus with Volta's faceplate. One very big drawback of the electron tomography is that, in contrary with the computer tomography that we shown for the medical applications, we cannot tilt our sample all around. That means that we cannot get all the exposures from all the angles of our sample. One limitation is that when we have our sample holder in the column of the microscope, and this is a cross-section of our microscope where we have the pole pieces of the objective lens, and we are tilting our sample in the electron beam. At a certain point, we may hit our objective lens with our sample, because these pole pieces are quite close. So first, what we need is a very special setup of the microscope that will have a quite large gap here and allowing high tilts for our sample holder. Yet this is not solving all our problems, because after some beam sample tilt, also the sample itself or the holder itself will limit us from acquiring our image. For example, the grid bars or the clip rings that we have around the sample may get in the way of the electrons that are passing through our sample, and therefore limiting the useful tilt range plus the useful imaging area on our sample. What this will end up is that we cannot rotate our sample into a 90-degree rotation, because we are not able to get image from this. Therefore, this ideal version of all-around rotated sample and getting images or transmissions images from the sample is idealistic and not possible in our setup. But if that would be possible, then if we would have a small ball and we would reconstruct it, we would get a very nice image of a ball that would be completely circular without any missing information. However, we have a real stage. The real stage you can tilt when you have a very good sample holder in ±70 degrees. It's more usual to tilt it in ±60 degrees. And what you will get is some missing part. This part was not exposed because we could not tilt our stage to this position, and therefore we are not acquiring at this tilt angle any useful information. What we will end up with this is that in the XY plane of our tomogram, we will have a very nice Fourier transform, whereas if we take it from the side, from the XZ plane, we will see that in the Fourier space we have a wedge of missing information. This is called the missing wedge in tomography, where in this place, in the Fourier transform of our images, we don't have any supporting information for the reconstruction. This is because at this angle our sample was not exposed at all. That means that this information was not recorded, and this information cannot be recovered by any method. Because this is a missing wedge in the Fourier space, it's not affecting our image only in the real space, or well, it's affecting every single point in the real space, because as we told, every point in the Fourier space every single point in Fourier space will affect all the points in the real space. So if we have a missing information, all these points are affecting all the points in the real space. Visually, what we will see when we reconstruct our sample that was previously a ball, we will have a sample that's a little bit elongated in the z-axis, plus visually it has a missing top and bottom, as you can see also on the cross-section. Yet the information, because it's missing in the Fourier space, is missing from all these points of the reconstruction. Now, one way how to avoid this missing wedge, or to include as much information as we can from our sample, is to do dual or multi-tilt tomography. For dual tilt tomography, we are not tilting our sample only over one tilt axis, but we are also tilting in the perpendicular axis. This will lead to a reconstruction that's not missing a wedge, rather it's missing a pyramid of information, and we are getting more and more closed circle or closed ball, and this reconstruction will more resemble our point of interest. There are even stages or sample holders where you can rotate your sample into many different angles, and therefore changing the tilt axis not only by 90 degrees, but you can incrementally change it by, let's say, 8 different positions. And then what you can do is that you reconstruct your sample where you will not have a missing wedge or a missing pyramid, but you will have something like a missing cone. So you will have more and more complete information about your sample. The problem, however, for us is usually the radiation damage. So to acquire all the tilts using all rotations of the tilt axis will require more and more damage on your sample. So for cryo samples, this is not really feasible. For stained samples, this is doable. Now, tomography data processing. We acquired our tilt series, and now it's time to process it. Some of the steps is the same as for SPA. Some of the steps will differ. At the very beginning, we of course can do some motion correction of the raw movie data frames of single tilts. This will be very important later when we will discuss how sub-tomogram averaging works, and there it's essential to do this motion correction. Whereas I have also to note that here we are not, we can do not only the motion correction of the frames inside the movie, or not motion correction, dose weighting of the frames in the movie, but we can do dose weighting of the finally aligned tilts inside the tilt series, because the dose will vary less in one tilt. You have only 4 fractions, as we told about, so the variation in between the first and the last fraction, the amount of accumulated dose is not that large. For the tilt series, in between the tilts, this dose variation is larger. After we have our tilt series, motion corrected tilt series, we are going to align our tilt series. This is because, as we told, there are no perfect stages. We are acquiring our tilt series using these tracking images, yet this is also not completely perfect. So first, what we will do is we will do a coarse alignment of our tilt series, which is actually done by a very easy cross correlation in between the neighboring tilts. So we will take our first tilt image, then we move by 1 tilt step to, let's say, +3, and do cross correlation in between these 2 images and see how the image needs to be shifted to match perfectly the previous tilt. Then we move forward to next and next and next tilt, so that we will have a nicely coarsely aligned tilt series. This, however, does not take in account the, for example, the inclination of the tilt axis over the image. For that, we need a fine alignment. That we are doing using generating a fiducial model. The fiducial model, we will see how it's done by tracking our fiducials. However, many times it's problematic to include fiducials, that there are some alternative methods to do that. Aligned tilt series are then post-processed. If we have our fiducials there, for example, the golden beads, they are very contrastful and making dark spots there. We can remove them by applying some min values in dispatches, or we also can do CTF correction if we are doing, for example, sub-tomogram averaging where we need it to achieve high resolution. Then when we have this aligned and post-processed tilt series, we can reconstruct our tomogram using different back projection algorithms that we will talk about. The finally generated tomogram is usually low in contrast. We need to do some tomogram filtering using different filters to increase the contrast for the segmentation or the visual inspection of the tomograms, as well as from usually the unprocessed tomograms, unfiltered tomograms, we can do sub-tomogram averaging so that we are refining our tomograms to, or subregions of our tomograms to a high resolution by averaging them together. Here I will show you how our tilt series look like when you acquire it by microscope. So you could see that even if we are using this tracking mechanism and defocus correction mechanism, our tomogram out of the microscope is still a little bit shaky, and therefore we need to do at least a coarse alignment. What we will get after this correlative coarse alignment is a nicely aligned images of tilts, that they are nicely rotating along the tilt axis. Yet, as I told, this is not perfect. Therefore, we need some fiducial based alignment or fiducial model to create a perfect alignment. If we have samples where we can include our fiducials, that's very feasible to do that, because these fiducials are creating very dark spots on our sample, and these dark spots we can very nicely trace or track in our image. So nowadays the programs automatically find these dark spots and then track how these spots are moving in between the tilts. So actually the software finds these spots on the first tilt, then it looks at the second tilt and look where this dot is, the dot is placed, and then it's interpolating the trajectory of this dot over all the tilt series of the image. When this is done, then what you will get a projection model, you will get a model that's showing how our fiducial is moving by tilting of the sample. And if we know how these fiducials are moving, we have a very, very precise track of the rotation and movement of our sample. Also, by this, you can predict if the tilt axis is perpendicular or not to your image. As we told, usually your tilt axis, if you tilt your image, is not perfectly perpendicular with the x or y axis of the image, so there is always some angle, and this angle can be estimated using this fine fiducial based alignment. What's also very good with the dark spots of the fiducials, that this allows us, in fact, sub-pixel precision of the alignment, because we are not only looking for the center of these dark spots, which because the fiducials are not perfectly spherical, we are also calculating the residues in between the consecutive alignments of the spots on the tilts and trying to minimize this, and therefore by the end we can get a very nicely estimated rotation model of our sample. But what if we don't have any of our fiducials because we forgot to add them when we prepare the sample? That's one case. The other case is that we could not put it there. For example, if we are having our cells, we are freezing our cells, we can freeze our cells with fiducials. Nevertheless, when we will thin our cells using a focused ion beam in the SEM microscope, we would mill away all the fiducials that are located on the surface of the cells, because we are taking a lamella that's located inside the cell. So for the lamellas, we cannot include any fiducials that will help us for tracking of the tilt series. For this, we have so-called patch tracking. What we are doing is that we are splitting our image into patches. Here we are splitting it to 4 by 6 patches. And these patches are then cross-correlated in between the tilts of the tilt series. So this is very similar to coarse alignment. Nevertheless, here we are not coarse aligning the whole image of the tilt. We are coarse aligning overlapping patches of the single tilt images. What's important here, this is usable only if we have a sample where we have enough information to cross-correlate the information in between the patches. Here we have some virus particles, and we can see that inside the patch we have few particles that gives us enough signal for the cross-correlation with the next tilt. However, if our area is such that there is only noise in the patch, this patch could be very hardly cross-correlated with the next one, and will end up in a very shaky movement of the patch. Then these patches actually are serving for our fiducial model. So you can think about every single center of this patch as a fiducial particle, and then you can fit on, depending on the movement of this patch over the tilt series, a trajectory model that will describe how your images are rotated. This is, however, less precise than the fiducial base model. Here you can see how nicely we can track the patches, but what you can see is that our patches are not producing that nice straight trajectories as the fiducial model did. However, we can nicely see where's the rotation axis, and here we are rotating, we are looking through the rotation axis, and we can see that some of the patches were very nicely tracked, yet we can also see a little bit of patches that were tracked with some haziness. Usually these points need to be removed to have a perfect reconstruction or perfect alignment of your tilt series. Now, after you have your fiducial alignment or fiducial based alignment, you can see that our image is not anymore perpendicular to the image axis, so the image is a little bit rotated. This is because of the tilt axis rotation, as we told about, and we have a very nicely, very precisely aligned tilt series of our sample. This then can go to reconstruction. And tomographical reconstruction relies on several methods, as back projection, weighted back projection, or the SIRT, the simultaneous iterative reconstruction technique. We already talked about in the previous lectures about how back projection works. Here we have an image of 3 dots originally, from which we have projection images under different angles. And because this was a 2D image, then the projection of the 2D image will be actually a 1D profile. And if we align all these 1D profiles at a certain angle at which the projection was done, and we make a back projection of this profile into a 2D image, we will get intensities of the original 3 dots at the correct places, yet around we will have some extra information that's not summing up well. This is because there was no weighting applied during the back projection process. And the reason for that is that the low frequencies in our projections are overrepresented in favor of higher frequencies. Therefore, the lower frequencies are giving us some haziness in the back projection process. Here you can see some illustrative image where you have the original that was projected under many different angles, and then back projection was done. This back projection gives us a very nice image of the original object, yet there is a very low frequency or low resolution haziness around the head of Einstein, which can be removed if our original projection data that we projected will have downrated low frequencies, and that will bring out more the high frequencies that you can see here in the weighted back projection model. So nowadays, usually if you are doing tomographic reconstruction, then you are doing the weighted back projection method of it. And the last one is very interesting, the simultaneous iterative reconstruction technique, which is iterative. Therefore, it's more time consuming and more computational intensive. What we are doing is that we are starting with some weighted back projection of our tomogram. We have a reconstruction of our tomogram, and from this tomogram, we are projecting into the original direction of our tilt series a projection of the tomogram. Now, because the reconstruction of the tomogram is the sum or the sum of the projections from all the tilt series, the image that we projected in a certain direction, this one, will differ from the original image that we used for the back projection, because the back projection, the reconstruction, is not only from the original image, but from all of them. That means that this difference is the error between the reconstruction and the original tilt. If we take this error, where, for example, in this pixel, we have in the original projection image tilt image 99 value, and the projection only gives us 87, we are taking this difference as an error of the back projection. And now what we are doing is we are correcting for this in our reconstruction the way that actually we are in fact back projecting the difference error to the original volume. And this will give us a more precise volume, yet we can iteratively going back, making a new projection of this corrected volume, again see what's the difference between the original projection and this corrected reprojection, see the difference, and then again back projecting the difference. This we are doing not from a single tilt angle, but from all the tilt angles. This makes it a little bit more time consuming, yet it will give us nicer reconstructions. What we will need to do is to find the correct amount of iterations that will lead to nice reconstructions, yet we won't waste too much time on it. This is where I want to show you how a reconstruction of our tilt series that we already aligned will look like with the weighted back projection process. We now scanning through from the top to the bottom and bottom to the top in the z-axis. We can see our virus particles in all of the layers, yet these particles are not very contrastful. If we do the same with SIRT back projection technique, we can see much nicer reconstruction, but this reconstruction obviously took a lot longer time to reconstruct. We can also see that our particles are not only round, but we have many fluffy spiky particles. We will use them for later stages of processing. Now we have reconstructed our volume. If we take a cross-section of our volume and look from the XZ plane, we can see that our volume, of course, suffers from the missing wedge. So all our things are elongated in the XZ plane, whereas they look very nice roundish in the XY plane. This is also supported by the Fourier transform that we see in the XY plane. We have a nice, very complete Fourier transform, whereas in the ZX plane, we can see nicely that there's this missing wedge artifact or the missing information in this wedge, which is affecting all our voxels in the real space. Now we have the tomogram, it's time to interpret it, and the problem with the tomograms usually is, as we already see for the weighted back projection tomograms, that they are very low in contrast. This is because we applied very low amount of electrons per every tilt in the tilt series. So we need to process or filter somehow our tomograms. The easiest filter how to increase the contrast is usually a low-pass filter. As we told about previously, Fourier space cropping is increasing the resolution because we are cropping off our high frequencies and letting to pass through the low frequencies. which is usually carrying the low resolution information, therefore increasing the contrast in our micrograph. Sometimes it's also needed to use high-pass filters. We know that the high-pass filters are usually used for edge detection because the edges are encoded in the Fourier space by high frequencies. Median filters, very similar to low-pass filters, again blurring our image. Here you can see, for example, the application of low-pass filters or Gaussian low-pass filters on an original slice of tomogram. That's a single slice from a tomographic reconstruction. What was previously very often used was a nonlinear anisotropic diffusion technique, which was a kind of balance between losing the information, the high-frequency information, yet increasing the contrast. This was a technique where at least two parameters needed to be fine-tuned, and this was empirical, so you needed to do it by hand, number of iterations of this procedure, and the amount, so-called K factor for that. Nowadays, it's very favorable to do this neural network-based denoising with noise-to-noise model or a unit model, where you are actually training your neural network on the noise data from your tomogram, and then you can do some denoising where you can see that you will get superior results to the results what you have from a Gaussian low-pass filter. When you have this nicely visualized tomograms or post-processed tomograms, you can go with visual inspection, what is located where, or some localizations, or you can segment your tomogram by annotating and extracting segments of the points of the interest of the tomogram. Usually on unfiltered tomograms, you can also perform sub-tomogram averaging to have high resolution structures out from the tomogram. This is just a showcase to show you how a nonlinear anisotropic diffusion filter works. This is the tomogram before the application of the filter, and here we see the tomogram after, which looks very nice, yet the high frequency information is very suppressed in this processing, yet it performs better than the easy low-pass filtering. Now segmentation, what it does is that you take your tomogram, and on every slice of the tomogram you are annotating the parts, you are connecting the connected areas and making so-called segments of them. Here you have a bacterial cell which is attacked by some phages, and then you can segment each parts, which you usually judge where are located ribosomes, where are located some chemoreceptor arrays, membranes, and cell walls. Some of the parts of this tomogram were done by so-called placeback. We will get at the very end of this presentation of this lecture what the placeback of the molecules is. So segmentation is a very tedious process. It's annotating usually manually the parts, although nowadays it's starting to be more and more automated. So you are connecting continuous segments, either by manual drawing into the tomogram. You are taking a slice of your tomogram, and by drawing lines or objects into this tomogram, you are creating a separate layer where you are kind of annotating the parts depending on the features. There are some filters, thresholding filters, that are helping for this. Usually the main problem here is the missing wedge artifact, which limits the interpretability of the features on the top and the bottom of the tomogram. We can use also semi-automatic approaches where we can, by correlation, annotate simultaneously multiple parts of the tomogram, or we can simultaneously annotate multiple slices of the tomogram. So, for example, you are annotating a membrane of the cell, the cell wall of the cell, and you have to do it for every single tomogram section, which can be, for example, 1,000. But with semi-automatic method, you are annotating it on the first one, and it's automatically annotated on the next 10 slices, following 10 slices as well. So this speeds up a little bit the manual drawing. Of course, nowadays for image analysis, it's very usual to use convolutional neural networks. This is based on training the convolutional neural network on a part of your data set. So you take just a subset of your tomogram, you manually annotate the features there, and then let the neural network to train on it to distinguish between the features. This first takes some time to manually annotate it. Then it takes a long time to train the neural network, but then it's very fast for the segmentation of the whole tomogram. Problem with it is that nowadays still there is no general model that you would input for the convolutional network, so that we would have a library of models, that we have a library where we select that we want to find all the ribosomes, we want to find the cell walls, we want to find the membranes. Every single model works usually only for the tomogram on which it was trained. So for the next tomogram, for other tomograms, you have to retrain the model with, again, manually annotated part of the tomogram. Now, not only the segmentation or the visual inspection is the way how we can get useful information out from our reconstructed tomograms. Sometimes there are very heterogeneous samples that we cannot reconstruct by SPA analysis, but we can do it with tomographic analysis, because in tomographic analysis we can align 3D volumes instead of 2D projections. So sub-tomogram averaging is something very similar what we are doing in SPA when we are averaging projections of the images, yet it is a little bit computational harder because we are aligning subvolumes. We are in fact boxing out our areas of interest as subvolumes from the tomograms, so-called sub-tomograms, and then we are finding the correct orientation of these sub-tomograms and averaging them together. This, however, has some specificities that we will discuss now. By averaging, we always increase the signal-to-noise ratio, and of course we can increase the resolution as well. Yet we need to be aware of that every single sub-tomogram that we have is suffering from the missing wedge artifact in the Fourier space. Now, as I told, for not that much for the tomography and visual inspection of the final tomograms, but for sub-tomogram averaging, the tilt dose weighting is very important, because our tilts are heavily damaged by the radiation. We need to heavily downweight the amount of high resolution information in the higher tilts. This is done by the very same process as we already discussed as the SPA, that we have some exposure-dependent amplitude attenuation, which depends on the spatial frequency and the accumulated dose of that of the current fraction. Whereas here we don't need to correct or to dose weight for the fractions. We can dose weight the summed tilts, which are of course kind of micrographs. So you can choose whether you will dose weight every single fraction or just the sum of the fractions, because every tilt from the tilt series contains usually 4 fractions, and these fractions are not carrying that much different information in the meaning of the amount of accumulated dose. Why this is important? Because if we would do our dose weighting the way we are doing in SPA, when we are starting the processing our movies with dose weighting, we would get already dose weighted tilt series. And then if we apply this into a software which is doing sub-tomogram averaging, many of the software is implementing themselves the dose weighting depending on which tilts they are actually working, and therefore you will end up with a double dose weighted data, which would have extremely attenuated high resolution information, therefore would not give you very nice high resolution results. So beware of that, whether to input into the software already dose weighted or non-dose weighted, which will be dose weighted by the software itself. Now, we already told about that the CTF is usually kept constant, or sorry, the defocus is usually kept constant over the tilt series. and therefore the CTF should be the same for all the tilt series. This is not true, because if you think about how the CTF works or how the defocus works, we have the focal plane and we have a thick sample of some thickness where we have our points of interest located in different height in correspondence to the focal plane. So we can have something higher or something lower. This is the same for a single particle analysis. What we are measuring and what we are fitting is the mean defocus of all the signal coming from our sample. Because our sample is very thin, usually around 100 nanometers, then the variation of the defocus in between the samples is not higher than, let's say, this 100 nanometers. Later we can, of course, refine it in a single particle process as well. Now, when we are taking our sample of thickness of 100 nanometers and we tilt it by 60 degrees, we will see that at the top and at the bottom we have a largely different defocus. So we cannot state that our sample is represented only by a single defocus in the middle, which is the focal plane. We have a large amount of information over and large amount of information under focused. That's why when we are doing a Fourier transform of this tilt series of the tilted sample versus the sample that's not tilted, in not tilted sample we have very nicely resolved tone rings, because the tone rings are coming from the information from every contrast full detail or sample in our point of interest in our sample. Whereas at the inclined, the 60 degrees tilted sample will have very weakly resolved tone rings because of the large defocus gradient that is going over our sample, and therefore we are kind of averaging all the CTF curves that are varying on this sample. To show it more in detail, here we have a fitting of an unconstrained CTF. What we see here is that we have the measured data, we have the radial average of the measured data, and then we have the fitting. We start at the middle tilt with a 0 tilt angle, and we see that we have a very perfect fit. However, the more and more we are moving to the sides, to the higher and higher tilt angles, the less and less high resolution information we can recover from the CTF. And at a certain point, the fitting is not fitting good anymore. So the fit is very badly fitted because we are not seeing the tone rings as we would from a single particle micrograph. This is true for into the both directions. So the higher we get, the worse the tilt will be. Also, what's happening here that usually we are giving a range for the CTF fitting, and because these high frequencies are included from our measured data, sometimes different defocus at the high frequencies will fit better than at low defocus, and therefore it will bias our defocus fit. To avoid this, we can constrain our defocus fit the way that we can very precisely estimate the defocus at 0 tilt, and then when we are incrementing our tilt series, we are restricting the range in which the defocus should be searched. As well, we are restricting to what frequencies, to what resolution it should be fitted. So here we can see that our defocus is fitted to lower resolution than here, as well as we will have a constrained defocus search range. And here you can see that from the same tilt series, you can get a very nicely fitted tone rings at low frequencies, plus ignoring the high frequencies, which are not very reliable at the high tilt angles. Now, when we have already estimated the CTF, it's time to correct for that. And again, this is true for SPA as well, that to correct, we need to find the correct defocus values for all the particles that live inside the ice. which we can do by some CTF refinement. For the generation of the tomogram itself, we need to take in account that our objects of interest are having different defocus depending on at what tilt angle they are acquired. So what we are doing is actually CTF correcting slabs of the tilt series, and these slabs, depending on what the slab has a mean defocus, is then with the CTF correction back projected to the final volume. Now we have a CTF corrected volume. We need to somehow locate our particles. It's a little bit harder to locate particles in a 3D tomogram than a 2D projection. As we already seen, for example, for XPA, we can do manual picking. This is possible, of course, also for tomograms. However, we need to be aware of that we are not seeing a single projection image here, but we are going slice by slice over our tomogram. That means that we don't need only to locate X and Y coordinate of our template, of our sub-tomogram, but we also need to precisely locate the center of this particle in the z-axis. And this is quite tedious to find where in the z-axis the center of the particle is. Nevertheless, when we don't have any known template available, we are boxing something new. This is routinely done by manual boxing. And also when we are curating automatic template matching results, we need to manually go through all the automatically picked boxes which have many false positives. For the automatic template matching, it's usually based on cross-correlative methods. We need a template. This is sometimes not a problem because, for example, we need to find some ribosomes in the cell. Then we can use a general model of a ribosome, a map of the ribosome that we will match against our 3D volume. The problem here is that it's quite computationally intensive because we are looking for a 3D volume in a larger 3D volume, and actually we are doing a cross correlation over all the volume with a certain sampling rate of all the possible orientations of our template, because the template is not oriented all the times the same orientation inside our tomogram. The good thing about template matching is that it produces not only coordinates, as it's done, for example, for the SPA in 2D when you are doing some particle picking automatically. It also produces you the best fitting orientation, because we are doing some orientational search, not only lateral search. For the best fitting or the best correlation, we know the coordinates x, y, z, and also know the best fitting orientation. This then can serve us, for example, for generation of an initial model, which also for sub-tomogram averaging needs to be heavily low-pass filtered, not to be biased by the input what we put there. This is just a showcase how, for example, template matching of this spiky structure located in our tomogram of virus particles, which have some spikes on their surface, looks like. What we see here is a correlation map of our template matched spikes, and we see that there are nicely visible white dots, high correlation areas on the surface of our particles. Also, if we know the positions, we can show here we have a tomogram of nice spiky particles, wire particles. We perform the template matching with the template of that spike, and now we can see not only the X, Y, Z position of this, but we also can color these positions by cross correlation. And because usually the template matching algorithms suffer from many false positives, you have to somehow hand curate this data and remove the false positive particles by hand. Now we have our subparticles, sub-tomograms. These sub-tomograms we extract from our tomogram, and we can do sub-tomogram averaging. It's again an iterative process as from the SPA refinement, where we start with a low-pass filtered initial model. And then with some global and local searches, we are looking for the best orientation of our sub-tomogram against the initial model or the reference. Then when we find the best orientation of our subparticles, sub-tomograms, we can average them together, generating a new initial model, new reference, and then repeat it until we don't see any improvement. A problem with the sub-tomogram averaging is that it's computationally very expensive because we are not aligning, we are not looking only for the Euler angles of the projections, we are actually aligning already a 3D volume and on a 3D volume, and that needs to look for the orientations, the 3 Euler angles, plus all shifts in X, Y, and Z direction. For this, nowadays, there are established softwares for cross-correlation based methods and maximum likelihood methods. I have to say that so far the maximum likelihood methods are not that well established as for the SPI, but they are making big leaps. We will see in the future how they will produce better results than the correlation ones. One other thing that we have to take in account that for all these techniques, for the cross-correlation and maximum likelihood methods, we need to compensate for the missing wedge artifact, for the missing wedge effect. Because if we would do only cross-correlation based on the missing wedge, based on our uncompensated data, then the missing wedge in the Fourier space would correlate the most, and all our particles would not be aligned by the information outside the missing wedge, but by the missing information inside the missing wedge. Because it's very computationally expensive, we need to speed up somehow our calculations by, let's call some tricks. That's usually based on that you start with heavily binned particles, and in these procedures this has to be done manually. So you start with some heavily binned particles and doing some low resolution alignment. Then gradually you are unbinning and unbinning your particles. After a certain stage, you will get to some binning where you can do on local alignments, because time-wise and memory-wise, it would be not feasible to do global alignment with unbinned particles. This is just one of the implementations, how you can do it. You have your reference, you apply mask on your reference, rotate your reference to one of the angles that you are, or one of the orientations that you are interested in, whether it fits or not fits the best with your sub-tomogram. You apply the missing wedge on this reference, and then you can cross-correlate your sub-tomogram, which is correctly low-pass filtered to a certain resolution. And of course, from different orientation shifts, you can generate a cross-correlation map, and finding the best orientation from every single of your sub-tomograms, then you can create a new reference and do it iteratively. This is just to show how you start with the generally low resolution spike of your wire surface, and then gradually by unbinning and correctly orienting your particles, averaging them together, you get to higher and higher resolutions until you get no further improvement. This way you can actually get to very decent resolutions. Nowadays in this map you can see already the amino acid chain of the protein. Nowadays there are 3 angstrom resolution sub-tomogram averaged structures available already. Now, another advantage of the tomograms over the SPA or the single projection images is that it is in 3D. So if we know the positions of our sub-tomograms and we have very nicely refined their orientation to the correct orientation, we can place back our images, or sorry, the sub-tomograms or sub-tomogram average into our original tomogram, and see the localization and the features that we can uncover with this procedure. This is, for example, how I told you that you can template match in your cells for example, the ribosomes, and instead of segmenting the ribosomes, you are placing back the sub-tomograms of the ribosomes into the tomogram so that you don't need to segment your cells by all the details. This is a placed back refined spike of our viruses, and we can see that our particles are very pleomorphic. They are very irregular. This was the reason why this sample was not working well on single particle analysis. And from our placebacks, we can see that how the particles are wholly and not regular. If we take just one of the particles, we can nicely see that we only replaced a single spike placed back into our tomogram, yet the orientations and the shifts of them created a very nice net of interconnected spikes, which extremely well corresponds with the low resolution reconstruction from the SPA, because it's also showing you some of the features that were visible on the SPA particles. So we are getting to the conclusion of our lecture. We talked about electron tomography, its advantages and disadvantages, why it's good and why it's sometimes not feasible to do electron tomography. We touched a little bit the sample preparation, which of course is needed for the electron tomography, as we need electron transparent sample. We told about how data acquisition is needed to properly be set up. We touched the data processing, including the sub-tomogram averaging. The future of electron tomography, because electron tomography is younger than the SPA and less established than the SPA, is sub-tomogram averaging in situ, which you take your cell, taking your tomogram, a tilt series of your cell, reconstruct a tomogram, and then you take features from your cell and average them together. That is how you can localize sub-tomograms which you are interested in directly in situ. Also, because as we told about that in SPA we are aiming to collect as much data as we can. Here the speed of acquisition is limited because of the tilting of the sample. There are new procedures which are speeding up the data acquisition, whereas previously we needed around 20 to 30 minutes for one tilt series to acquire. Nowadays we can speed this up by beam shift or image shifted acquisition up to 5 times. Data processing in or tomogram electron tomography is still very manual. The approaches are to more and more automated this data processing, so that after the acquisition you won't get unaligned tilt series, but you will have automatically processed tilt series up to the generation of some basic tomogram. We already told about that people are also trying to combine tomography and SPA by getting the zero tilt image as a micrograph for the SPA. This is going to be developed more and more. And the last thing that's very often mentioned nowadays is correlative microscopy, where we are combining fluorescent microscopy and electron microscopy, getting rid of the disadvantage of the electron microscopy, where we cannot identify the parts in the tomograms by some labeling, whereas in fluorescent microscopy it's very easy to label parts or some features in the cell by fluorescent labels. Therefore, if you can do fluorescent microscopy under cryogenic conditions, and then you can transfer your sample into electron microscope, you can correlate the images of fluorescent microscopy with the electron microscopy tomograms and have a high resolution reconstruction of the features. And that's all. Thank you for your attention, and see you next time.